All right, so welcome back. Chapter 19 is going to be the final chapter we're going to cover this semester. So let me at least start it here today. And chapter 19 deals with redox. So we already talked about redox reactions. Redox reactions are electron transfer. And so what we're going to do in this particular chapter is we're going to look at one big application of redox, which would be electrochemistry. And we'll review redox reactions in general as well. And so this chapter starts off dealing with just the application here, electrochemistry. In electrochemistry, we have electrochemical cells. And so let's maybe talk about that first before we get into the specific application here. And oops, go with that. Electrochemistry. Sorry for the sloppy writing, but we have electrochemical cells. We have two types of electrochemical cells. Electrochemical cells. The two types of electrochemical cells, one would be a voltaic or galvanic cell, or a battery. And basically, these are all batteries. The other type of cell is called an electrolytic cell. And so these ones, we have a redox reaction, and this redox reaction generates electricity, basically. In the electrolytic cell, we use electricity to generate redox reactions. These redox reactions are unfavorable, so this is like an uphill redox reaction. So we're forcing, let's say we want to get all bicyclists to the top. Well, it's possible. We can use electricity. If everybody had an electric bike, everybody can make it to the top kind of thing. And therefore, we get an unstable situation where we're going up from higher energy versus lower energy. Whereas this is just a downhill type deal, where we're going to go downhill, and all the energy since energy is conserved, all this energy that's released can be generating electricity here. So this is a voltaic cell or battery, and so we'll just call it a battery here. And so this reaction is going to generate electricity here. And so how does a battery work here? And so we'll take a look at the parts of the battery and how the battery works. 1 minute. So the most important thing about a battery is we separate the oxidizer from the reducer. And so over here on the right, we have the oxidizer. And the oxidizer here is the copper 2+. So what copper 2+ wants is it wants electrons. It wants 2 electrons. And then it forms copper metal. And so on one side of the cell, we have the oxidizer. On the other side of the cell, we have the reducer. And the reducer, in this case, is zinc. And so where's copper going to get those electrons? It's going to take them from the zinc. Zinc is going to lose 2 electrons to form zinc ion. And what we have to have is we have to have these electrons go through an external wire. And so the electrons are going to travel through this wire here to go from the reducer over to the oxidizer. When it goes through the wire, the oxidizer is pulling it so it can power something like a light bulb or a motor or something like that, with this flow of electrons. And so the copper 2 is pulling the electrons over to it. And now what's all this other stuff? All this other stuff is to make the battery work, essentially. Because over here, we're generating zinc ion. Now, zinc ion is going to be hydrated, so that's going to help stabilize it, but it doesn't stabilize it enough because there's no anions here. And so we're missing anions. And over here, we're losing copper 2 because what's happening is the copper 2 is going to start to plate on top of the surface of the copper metal. So this is going to grow bigger and bigger because what's happening is the copper Q actually is going to plate solid copper. And the zinc, this one's shrinking. Look at it, it's getting smaller and smaller. And so this is curving away. It's curving away because the zinc solid is going to zinc ion. And so here we're losing cations. And so here we're missing anions because we're generating cations. Over here we're losing. And so what's happening is there's anion in here too. And normally the anion's like sulfate. And so pretty soon the sulfate has no partner because if we lose the copper too, then we just only have anions here. And so what has to happen is this. This is something called the salt bridge. And in the salt bridge, what we have is, for example, here, sulfate is contained in the salt bridge. The sulfate will come in here and pair up with the zinc. And so that'll neutralize the charge. They don't precipitate, but overall the charge will be neutral because there'll be sulfate. For every zinc 2+ that's produced, one sulfate will migrate over here. And then over here, each time we lose a copper 2, then 2 potassiums have to come in here to pair up with the sulfate that's already existing. So we got 2 potassiums. Otherwise, we lose electrical neutrality. So the job of the salt bridge is just to be an ion supply source. And so here we need, for each cation, we need an anion that's produced. And so the anion is going to come from the salt bridge. And over here, each time we lose a copper 2, we have to replace it with cations. Otherwise, the sulfate will be alone. And then the 2 potassiums come down. And so the salt bridge also maintains neutrality too, because for every sulfate that moves to the left, 2 potassiums have to move to the right. And so the job of the salt bridge is to make sure that the charge doesn't build up too high, because if the charge, we call it space charge, if the space charge builds up too high, that's going to stop the battery from working. And so there are 2 circuits here. There's the external circuit, which electrons flow, and an internal circuit where the ions flow. You don't have to necessarily know that, but that's kind of the basics of how the battery works. We have some other names. The salt bridge we talked about. And electrodes, we need to talk about that next. And so the electrodes, so over here, this is an electrode, this piece of metal here, and this is a reactive electrode because zinc is the reactant and it's an electrode. Electrode supplies the electrons in this case, or consumes electrons over here, or supplies them to the oxidizer. So over here, the electrode gets eaten away, the zinc, and as that the electrons flow. Let's say the electrons flow through the electrode here into the wire. There's a copper wire here. Copper is an excellent conductor of electricity, so it's often used as a wire. And that's going to flow over to the copper electrode. At the copper electrode, the electrodes are fed to copper 2 ions. So the electrons are fed to the copper 2 ions, precipitating out the copper solid. So that's what we have over here. And so the job of the electrodes here is just to either be a reactive, like the zinc, and then also the electrons go through, or to feed. In this case, this is what we call an inert electrode because copper metal is not reacting. Copper ion is. Copper metal is a product, but we're using the copper to feed the electrons to copper 2. Now, the electrode over here should not react directly. So, for example, if we use the zinc electrode over here, then electrons would flow directly to the copper 2 and would bypass the external circuit altogether. So we don't want to use, in other words, we have to use something that's not going to be oxidized by copper 2 over here. Otherwise, we're going to get direct reaction. What we want is indirect reaction. So this has to be an inert electrode. And this electrode is called the cathode more specifically because the cations go to this electrode. And this electrode is called the anode because the anions will travel to this electrode. That is, for every Zn2+ is generated, we need the sulfate. And so the anions travel to this one, cations travel to this one, therefore cathode, anode. Now, anodes where the electrons are being generated, so that gets a negative charge because that's where the electrons are generated, and cathode is where the electrons are consumed, so that gets a positive charge. The electrons are being pulled towards the cathode because of this. And so it's a charge. Okay. Okay, I basically talked about these features here. All right, we need to talk about the half reactions, oxidation and reduction once again here. All right, this is what we call the reduction half reaction. The oxidizer undergoes the reduction half. And over here, the reducer, this one is the oxidation half reaction. And so if we combine the two half reactions, this half reaction right here, and this half reaction, we get the net redox reaction. We have to just make sure the electrons cancel. So 2 electrons are generated over here, 2 electrons are consumed over there. So this will be the net redox reaction down here. There's driving force for this. We're going from stronger to weaker oxidizer. That's why it's this downhill. So we're generating electricity for this particular reaction. Now, it gets confusing. And so there are certain mnemonics. Oil rig, oxidation is loss of electrons. So we can say oxidation is loss of electrons. Reduction is gain of electrons. And so here, reduction, gain of electrons. Who gained the electrons? The oxidizer gained the electrons. And so the terminology is like this. If you were a victim of robbery, you were robbed, but you weren't robbing, something like that. And so this one, you have to think about, and eventually it'll click. The oxidizer is reduced. The oxidizer causes oxidation. And so who got oxidized? The zinc got oxidized. So this is the oxidation half reaction. And the reducer gets oxidized. And the robber is not the same as the person who was robbed. And so the oxidizer is like the robber of electrons, and the zinc was the victim of that robbery. And so the terminology is complex sometimes. These are the half reactions here. When you add up the 2 half reactions, the electrons have to cancel, we get the net reaction here. This is electron transfer reaction. 2 electrons are transferred in this particular reaction. And we look for the driving force. So we're going from a zinc, which is a reducing agent, copper, which is an oxidizing agent, to this would be oxidizing, this would be the reducing going backwards. And so we have a conjugate relationship here too. Zinc is the reducer with its conjugate oxidizer, zinc ion, and copper ion with its conjugate reducer, which is copper metal. But we look on the redox chart, and it turns out copper 2 is a stronger oxidizer than zinc 2. And zinc is a stronger reducer than copper. In other words, copper is less active, it's a weaker reducer than zinc. Zinc is more active. This is here, we don't want it to react directly. Here's a direct reaction. So what they did here was they just took a chunk of zinc, the silver metal, and dipped it into copper 2 sulfate. And then you can see the black precipitate on there. The black precipitate are crystals of copper metal. As the crystals of copper metal grow, then you get that distinct color. But what you can see is the copper 2 gives the blue color in the solution. Over here, the blue color has essentially disappeared. And the copper 2 ion is being... And so this is direct reaction, and the electrons are being transferred directly. We don't want the electrons being transferred directly. And so we have to separate the oxidizer and the reducer. Here, the oxidizer and reducer are undergoing direct reaction, and therefore we're not going to generate any electricity in this particular cell. Here's another example of direct reaction as well. In this case, the silver ions are oxidizing copper metal. There's a clean piece of copper metal on the wire. And the silver, you can see the silver crystals precipitate here. Looks like cave-like formations. But those are silver crystals. Silver forms dendritic crystals, which look like tree branches. So this is a voltaic cell. We need to keep it separate. And so here they're keeping the oxidizer separate from the reducer. Therefore, the reducer is going to lose electrons, and the electrons are going to travel through the wire to the oxidizer. And the oxidizer will consume the electrons over here. And so basically, this is what's happening. This is a voltaic cell where there's a driving force. And so voltaic cells, certain things, the anode is where oxidation occurs, and that's where the electrons are generated. And the anode gets a negative, and the cathode is a positive. This is where reduction occurs, and that's where the electrons are being consumed. And we talked about half reactions or half cells. Each of those are half cells. The half cells are connected by a salt bridge. The salt bridge maintains electrical neutrality in the solutions. Otherwise, you have a safe charge buildup, and that prevents further reduction from occurring. The next type of cell are electrolytic cells. The electrolytic cells use electricity to drive unfavorable reactions. And so this consists of two identical electrodes immersed in electrolyte. Electrolyte is a solution that conducts electricity by ionic movement. So there's some electrolysis that occurs. And so let's skip all this minutia here and just look at an electrolytic cell here. Now, electrolytic cell, we don't have to separate because nothing occurs spontaneously. These are all like non-spontaneous reactions. We have to force them to occur. And the way you force it to occur is by using a battery or power supply. In the battery or power supply, we connect one of the electrodes to the positive terminal. When we connect it to the positive terminal here, it's going to suck electrons in to the positive terminal. And then we connect the other one to the negative terminal. It forces electrons out. And so as this sucks the electrons in, the anode is always, negative. And so this negative is actually attached to that positive. And the anode is where the electrons are being generated. So electrons here are being generated by this half reaction. We have two chlorides. This will go to a chlorine, Cl2, plus 2 electrons. And so chloride is very hard to oxidize. I mean, we can eat this stuff. It's fairly unreactive. But you can force the chloride to react to generate chlorine gas by stripping the electrons. The chlorine gas will bubble out of here like this. As long as we turn up the voltage high enough, we need enough volts to do this. So we just power this up, and then the electrons get sucked into the power here and generates the chlorine gas. Out over here, the electrons get forced out. And they're going to force out, and it looks like this is molten sodium chloride. This is molten sodium chloride. Molten sodium chloride consists of sodium ions in the liquid state and chloride ions in the liquid state. And so the sodium ions will pick up the electrons here and make sodium metal. Now the temperature of this is going to be fairly hot, so it forms sodium liquid, which rises to the top here. We don't want the molten sodium metal to come into contact with the chlorine gas. So there has to be a barrier here. The barrier doesn't go into the molten, because the ions have to be free to move around here. The barrier is just to keep the chlorine gas from coming into contact with the molten sodium. The molten sodium is going to just collect on the surface of this. This is not very dense metal. We just got to prevent the molten sodium from coming into contact with chlorine. Otherwise, you're going to have a very violent reaction that occurs. So we're going to have sodium ions. Two sodium ions pick up these two electrons that were generated over here on the right to form two sodium liquids. And so these are the half reactions. And we add up the half reactions to get the net reaction. In this case, the net reaction is this. 2 sodium ions plus 2 chloride ions yield molten sodium metal plus chlorine gas. Now this is very uphill. When we look at it, sodium ion is a weak oxidizer compared to chlorine. Chlorine is much, much more powerful oxidizer. And as far as reducers go, sodium metal is a much better reducer than chloride ion. And so this is a very uphill. But the way we get everything to go uphill is by using power, external power source. And so we need the power in order to do this. And so what electrolysis is used for generating highly reactive chemicals like sodium metal. Sodium metal is a highly reactive chemical, and chlorine gas is a highly reactive chemical. The other uses for electrolytic cells are like for electroplating. You can force metals to plate on to things. This is electrolysis of sodium chloride, just what we saw before here in a different figure. And then we have, okay, in order to better understand redox properties, so now we're going to go to redox reactions in general. Redox reactions and properties. But we need the oxidation number or state. That's very important. And that gives us some insight into, you know, the redox chemistry here. And so these are the rules for assigning oxidation numbers. The oxidation number of an elemental substance is 0. Monatomic ions is this charge. Anything combined with oxygen is -2 usually, except when combined with hydrogen, you know. And so typically oxygen is -2, but there are exceptions. In the peroxides where it's -1, the superoxides, which we never talked about really, is -1/2. And like in OF2, it's +2, which is kind of unstable. And so there's a certain sequence we do in the rules. So combined hydrogen, we always assign +1. Therefore, we don't have to memorize, when is oxygen -2, when is it -1, because if we do hydrogen in the group 1s as +1, then things work out. But hydrogen can be +1, 0, or -1 in hydrides. So what are the oxidation numbers? Well, oxygen's -2. We have 2 of them. That's -4. Therefore, carbon's got to be +4. So carbon's +4. Oxygen's -2. So there's some exercises writing formulas with different oxidation numbers. Then looking at changes in oxidation numbers. In redox, we're always going to have a change in oxidation numbers. All right, so here, this is useful to determine. This is kind of a complex redox reaction. This is what happens in automobile batteries. And so elements in elemental form are 0. Let me blow this up so you can see it a little easier. So lead is an element, and therefore it's 0. And then here, lead and oxygen. Oxygen goes first at -2. We have 2 of those. It's -4. That means lead has to be +4. Over here, it's just monatomic. It's the same as charge, +1. Over here, we have oxygen versus sulfur. Oxygen goes first. It's more electronegative. So it's -2 times 4 is -8. -8 plus what gives us -2? This is going to be +6. That'll be it. And then, let's see. On the products, we have sulfate. So this is going to be +2. And this whole thing is -2, but it's -2 for the oxygen. -2 times 4 is -8, and that's +6. And that will give us a total of -2. This is going to be -2 and then +1 here. We've done oxidation numbers before, so I'm not going to spend too much time on this. But interesting thing happens. One of the leads loses electrons, and so we go from lead 0 to lead 2+, so it's lost 2 electrons. Another of the leads gained electrons, so we go from lead 4 to lead 2. And so we have lead gaining, that is, it's in the oxidizer, and it's reduced. Remember, reduction is gain, but the oxidizer takes them. And this is the reducer, the lead metal, and we're going from 0 to +2, so it's losing electrons. And so what they're saying here is lead is both oxidized. Oops. Let's see. Lead is both oxidized. Well, one of the leads is oxidized, the lead 0. It goes from 0 to +2. The other lead is reduced because it goes from +4 to +2. Reduced meaning gains electrons. Oxidized means loses electrons. Oxidizing agents and reducing agents here. In this case, oxygen's -2. We have 3 of them. This is going to be plus 3 here. And this is 0. This would be 0 elements in elemental form. This would be minus 2, and this would be plus 3 here. So the iron gained electrons. Each iron went from plus 3 to 0. And so it's an oxidizing agent, a species that takes electrons. Whereas aluminum here went from 0 to plus 3, so that lost electrons. That must be the reducing agent here. So oxidizing agent, reducing agent. Consider the redox reaction here. We have nitrate plus arsenic plus water yields nitric oxide plus arsenate plus H+. Determine the oxidation number of each element in the species. So here, oxygen goes at minus 2. Minus 2 times 3 is minus 6. Minus 6 plus what gives us minus 1? This has got to be plus 5. And then this is an element. In the elemental form, this is 0. This is minus 2 plus 1. Here we got minus 2 plus 2. Over here we have minus 2 times 4 is minus 8. Minus 8 plus what gives us minus 3? This is going to be plus 5. And this is plus 1. And so what happened here is nitrogen went from plus 5 over here to plus 2, so gained electrons, 3 electrons. And then arsenic went from 0 over here to plus 5, so it lost 5 electrons. Each one lost 5 electrons. And so we can label this stuff here. So this thing that takes electrons is the oxidizing agent. So let's go ahead and label this. This would be the oxidizing agent. The thing that loses electrons is the reducing agent. And so the oxidizing agent oxidizes something. So arsenic was oxidized as arsenic lost electrons, going from arsenic to arsenate. And then the oxidizing agent is reduced in the process. It gains electrons. And so it went from nitrate with nitrogen plus 5 to nitric oxide with nitrogen plus 2. So that's some of the terms. The strengths of oxidizing agents and reducing agents we get from the redox chart. And you should know the strongest oxidizer on the redox chart is fluorine. So this is the strongest oxidizer on the chart. And the strongest reducer, since we have a conjugate relationship, is down on the bottom right. This is the strongest reducer here, lithium. Lithium is an excellent reducer. And the conjugate relationship here holds. So if we look at fluorine, the oxidizer, its conjugate reducer, fluoride, is very weak. It's got to be weak. That is, it doesn't want to lose electrons. Once fluorine gains electrons, it holds onto it, so it's quite stable. And so the conjugate reducer is extremely weak if the oxidizer is strong. Likewise, if the oxidizer is extremely weak, so this is extremely weak oxidizer, lithium ion down here at the bottom, then its conjugate reducer is strong. So we have the redox chart here that we can use. And we can predict reactions based on this. And so what we do is we just get these are the half reactions we get. And so we're doing the reaction between cobalt and silver. And so we look for cobalt 2 on the chart here. And I see it right here. So we just copy this. And then the other reaction is between silver. However, silver is on the wrong side here. Since it's on the wrong side, what we have to do is we have to reverse this reaction for silver. And so if we reverse that reaction, it's going to be silver solid. Now it's on the right side because it's got to be on the reactant side. And so if we go from silver solid, we're going to form silver plus an electron. And so this is the one we're interested in here. And so that's what they do here. They just copy the half reactions here off the chart. And so from chart, say. And so this gives rise to the chart method. And then just add them. The problem with adding these is you can see that there are 2 electrons here, but only 1 electron's here. So we have to double the second one. That's what they're doing here. They're doubling it, so we get 2 electrons there. And then add it up. And you know it's balanced if the atom's balanced. 1 cobalt, 2 silvers, 2 silvers. But in addition to atom balancing, the charges have to balance. And so over here it's +2, and these are 0. So it's +2. And over here this is 0, but we have +1, but we have 2 of them, so it's +2. And so the atoms have to balance and the charges have to balance. And then we look for driving force. And so going forward, cobalt gains electrons. It goes from 2 plus to 0. So this is my oxidizer going forward. And this is the reducer going forward because silver goes from 0 to +1, so it lost electrons. Now going backwards, silver plus gains electrons. And so this will be the oxidizer going backwards. And cobalt loses going backwards. And so we're comparing the strength of cobalt 2 versus silver ion. And so we go back to the chart here. Here's silver ion, and then cobalt 2 was way down here. And so silver ion is stronger than cobalt 2. We go back over here. Oops, that's not what I want. What do I want? I don't want this. So this is weaker to stronger. This is also weaker. Silver, that means silver must be weaker than cobalt. Cobalt must be a stronger reducer. So let's just verify that. Oops, that's not what I want. Here we are. And so let's take a look at silver versus cobalt metal. So silver metal is here, and then cobalt is down here. So cobalt is stronger. And that's correct. And so we're going weak, weak to strong, strong. So this is not favorable. This is not favorable. So we do this like in an electrolytic cell. That could make it work. Or, you know, there's going to be some kind of equilibrium that's generated. There still could be product formation, just not a huge amount because it's uphill, particular reaction. Write the equation between lead and nitric acid and predict which direction is favored. So lead and nitric acid is like this. The first step is what we do is we inventory it. And so let me do this from the beginning, the lead and nitric acid. This is not going to be a double replacement type reaction. When we have oxidizing acids, we have to use what we say is the chart method. And so Pb plus HNO3, HNO3. It turns out if you do this as a single replacement, you get the wrong answer. I'll try to do this. That is A plus Bx. A plus Bx yields lead 2 nitrate plus hydrogen gas. Actually, maybe we should. Okay. When we compare lead with hydrogen, let's take a look. Which one's more active? And so the activity series is here. Lithium is the most active, and then we'll go down here. And the first one we'll hit is lead. Lead here is more active than hydrogen gas. Oops. So this is more active to less active. We expect a driving force here. Okay. is more active to less active. This is driving force. So some hydrogen gas can form. But we can also do this by a chart method. So this is single replacement. Now let's redo this problem by the chart method. And so what we're going to do is we're going to inventory it. So we got lead solid, and then nitric acid is strong acid. The strong acid is fully ionized in solution. So it's going to give us H plus and nitrate. And we're also going to have water. Water is present in all of these. And then we consult the chart. Lead is only on the reducing side of the chart, so it's a reducing agent. H plus is only on the oxidizing. Nitrate and H plus, that's on the oxidizing side of the chart, and water is on both sides. It's an oxidizing agent and a reducing agent, so, like amphoteric, like the acids and bases. It just, but there's no specific word for that. And so all I did was I looked at the chart. Lead is on the right side. It's a reducer. Okay, and then I go on to H plus. H plus is on the left side. It's an oxidizer. So I have H plus here. It's an oxidizer. But I also have nitrate and H plus here. It's nitric acid. And that's an even better oxidizer, even stronger oxidizer than just H plus alone. And then I have water. Let's try to find water here. Water is pretty weak either way. And so water, and I'm just looking for water alone, not water combined with a bunch of other stuff. Here, this is water's not alone, but this water's alone here. So I have water that's a reducer, and I also have water that's an oxidizer, but it's not shown in this chart. So I label it, and then I choose the strongest. So out of all these, which is strongest? It turns out that this is nitrate and H plus is the strongest oxidizer. And as far as reducers, the lead is the strongest reducer. And then what we do is we write out the half reactions. So for lead, I just copy it off the chart, but I have to reverse it. That is, lead goes to lead 2 plus 2 electrons. This comes from the chart. And then the oxidizer is, I just copy it, nitrate plus 4H plus 3 electrons yields NO, nitric oxide gas, plus 2H2O liquids. And then what I'm going to do is I'm going to combine these two. However, I have to make sure the electrons work out. And so the first one I see is 2 electrons here. And the second one I see is 3 electrons here. So what I'm going to do is I'm going to multiply the first one by 3 and the second one by 2. And so if I do that, then I'm going to get 3 lead plus 2 nitrates, get a negative charge there, plus 4H plus 3 electrons. Well, those 3 electrons, not 3, 6 electrons, sorry. I forgot to multiply by 2. This should be 2 times 4 is 8. And 2 times 3 is 6, so this goes 6 electrons. This is going to be 3 times Pb2 plus, so 3 Pb2 plus 3 times 2 electrons is 6 electrons, plus 2 NOs, 2 times NO, and 2 times 2 is 4 water. All right, and so this would be the net redox for this, using the chart method. And so this is what they have here, and this is where they get it. Now, when we do this chart method, we use the conjugate relationship to figure out the conjugate pairs. And so this is our oxidizer. Oxidizers take electrons. Therefore, this must be the conjugate reducer. Okay. This is the reducer here, the lead. And therefore, this is the conjugate oxidizer. And so we can label that, and then we can compare the strengths. So if this is the oxidizer here on the reactant side, and this is the oxidizer here on the product side, which one's stronger? So we're looking at nitrate and H plus versus Pb2 plus. So we go back to the chart and take a look. Okay, Pb2 plus is here. And then we go up. Nitrate is here. So nitrate's stronger. Oops, I didn't want to do that. So nitrate is stronger. And so we're going from a stronger oxidizer to a weaker oxidizer. And so the driving force is there. The 6 electrons get to cancel when they're out. All right, so this example of using the chart method. We can also do the zigzag as we did earlier, with the acids and bases. And this is the zigzag method here. What we want to do is we want to go from a stronger oxidizer up here to a weaker oxidizer down here. So it reacts with anything lower than this. And so this oxidizer will react with any reducer stronger than hydrogen. And then it will be downhill. And downhill here. Downhill is the opposite direction here. So this is the zigzag method here. And so nitric acid is an excellent oxidizer. We can figure out what else can nitric acid oxidize, take electrons from. And so if we consult the chart here, we can see that nitric acid here will oxidize anything stronger than NO in water. And so anything stronger will be this way. So nitric acid can react with silver, that'll be downhill. Nitric acid can react with iron 2, that'll be downhill. Nitric acid can react with iodide, that'll be downhill. So all these are downhill. However, it cannot react with reducers stronger than, this is stronger. It cannot react with reducers that are weaker than NO. Because if it reacts with a reducer that's weaker than NO, then it's uphill. And so it's not good. These are not good. Whereas these are good here. And so we can use the chart. And so nitric acid reacts with all oxidizers stronger than NO. Silver, iron 2, iodide, copper, plus, hydrogen, etc. And so this is our predicting redox reaction, which we just did using this. Let's go back to this slide here. And so here's a comparison between acid base and redox. Acid base is the proton, this is Bronsted. Proton transfer, redox electron transfer. So you can read about some of the similarities and differences between that. All right, so the last section of chapter 19 deals with something called skeleton redox reactions. Oops, I guess this is too big here. All right, so what are skeleton redox reactions? Skeleton redox reactions, you have the major reactants and the major products, but it's not balanced, as you can see. Here we have nitrate is the major reactant, and the major product from this is NO. And these are what we call skeleton half reactions. And so this is one half. There's got to be another half, because in this particular half reaction, what we can see is what's going on here in terms of the oxidation states. So, okay, let's see if I can get this to line up. No, I can't get that to line up. So instead, I'll just write it down here. And so what's happening here is we have nitrate going to nitric oxide. And if we look at the oxidation states here, oxygen is -2. -2 times 3 is -6. -6 plus 5 gives us -1, that's net charge. So nitrogen is going from +5 in nitrate. Oxygen is -2. That means nitrogen has to be +2 here, +2. So nitrate is gaining electrons. If we're gaining electrons, this is the reduction half reaction. In the reduction half reaction, who gains electrons? The oxidizer. So nitrate is the oxidizer in this particular case, and this is the reduction half reaction. And so something's missing here, as far as what's going on. Now, let's see, next slide here. Next slide tells us how we balance it. And so one thing that's not balanced are the oxygens. Here we have 3 oxygens. Over here we have just 1 oxygen. We balance the oxygens by adding waters. Now that's an odd way of balancing. We don't add oxygen because that changes something more significantly. So here we're going to just add 2 waters. 2 waters will supply 2 oxygens. But now the hydrogen's screwed up because over here we had no hydrogens, and now we're going to have 4 hydrogens. And so we're going to balance out the hydrogens by adding H+. And once we do that, then we balance out the charge here. And so the way I set it up is a little bit different. So let's do it the way I would set this up here. And so I'm going to try to balance out the skeleton half reaction. So we got nitrate goes to NO. And so what I do is I first look at the nitrogen. The nitrogen is balanced, so we don't have to worry about that. Then we look at the oxygens. I have 3 oxygens here, 1 oxygen here. And so in order to balance out the oxygen, I'm going to add 2 waters here, because that will give me 2 oxygens plus 1 oxygen gives me 3 oxygens. So then it balances here. And then I balance out the hydrogens. Over here I have 0 hydrogens. Over here I have 4 hydrogens. In order to balance out the hydrogens, I'm going to add H+. So up here we'll just add 4H+. And that will balance out the hydrogens here. And then finally I'm going to balance out the charge. And so when I look at the charge here, it's +4 minus 1 gives me +3. And then this is 0, that's 0, so there's 0 charge. Now the way we balance out the charge is we add electrons, negative charges. So in this case, if I add +3 electrons over here, then the +3 electrons gives us a charge of -3, -3 plus a -1 gives us -4, +4 is 0. And now we'll add everything up. When we add everything up, I'm going to get 4H plus a nitrate plus 3 electrons yields nitric oxide gas plus 2H2O liquid. And this should be a balanced half reaction, and it's going to be a reduction half reaction. So this should be a balanced reduction half reaction. And we check atom balance first. And so make sure the atoms are balanced. 4 hydrogens, 1 nitrogen, 3 oxygens, 3 oxygens. And then we check for charge balance. +4 minus 1 is +3, -3 is 0. And so we have 0 on the left, 0 on the right. So this is balanced. In fact, the redox chart is a chart of balanced reduction half reactions. And so if we go back to the redox chart here, we can see this half reaction here. This half reaction is 1 nitrate plus 4H plus 3 electrons gives 1 nitric oxide plus 2 waters. And so this particular half reaction, I didn't have to balance it using the skeleton method. I could have just copied this. And so balance or copy from the chart. If I know that nitrate goes to NO, then the rest of it I can just get from the chart. But the problem is not everything is on the chart. The chart's not completely comprehensive, so sometimes these aren't on there. But in this particular case, this was on there, and I would have just copied it rather than figured it out. Well, if we have a reduction half, we also need an oxidation half. Somewhere those electrons have to come from, and that's what the species being oxidized. The species being oxidized would be the oxidation half. And so half this redox is missing. We just have the reduction part of it. Let's take a look at this next active example here. The permanganate ion is a strong oxidizing agent that oxidizes chloride ion to chlorine in an acidic solution. Manganese ends up as monatomic manganese 2 ion. Write the net ionic equation for the redox reaction. And so they give us the skeleton reaction here. So they give us the major reactants, permanganate and chloride, and they give us the major products, chlorine and manganese. And so what we do is we divide it into two skeleton half reactions. The two skeleton half reactions is chloride goes to chlorine. So chloride goes to chlorine. Well, that's on the redox chart. And so we could just copy from the redox chart. Copy from redox chart. That is, 2 chlorides goes to chlorine plus 2 electrons. It's backwards. The redox chart has chlorine plus 2 electrons yield 2 chlorides. But here we have chloride is the reactant, not chlorine. So what we'll do is just reverse this so that we make chloride the reactant. And so reversing this, we get 2 chlorides goes to chlorine plus 2 electrons. And so we want chloride as the reactant and chlorine as a product. Chloride's the reactant, chlorine is the product here. So that's why we reversed it. So it is on the redox chart, but we had to reverse it, which is not a problem. Now, permanganate and manganese 2 plus, is that on our redox chart? And so let's take a look. If that's on the redox chart, then I don't want to have to hassle with balancing it. I'd rather just copy it. That's not on the Chem 4 redox chart. Okay, it's not on the Chem 4 redox chart. Is it going to be on the redox chart in the Chem 1A redox chart? And so let me take a quick look here. Well, because if it is, then I'd just rather just copy it. And so redox, actually, I called it, what did I call it? Acid base redox chart. There we go. And so I'm looking for permanganate goes to manganese 2 plus. In fact, that's on the redox chart here. Do you see that? This is it. And so in this case, I'm not going to bother with figuring out. I'm just going to copy it off the redox chart. Permanganate plus 8H plus 5 electrons. So in this particular example, both of these reactions are on the redox chart. And so it's going to be permanganate plus 8H plus 5 electrons goes to manganese 2 plus 4 waters. And then I'll just add them together. And so here, they went through and went ahead and balanced it. And then we can add them together. Here's the adding them together. Adding them together is, one, we have to multiply by 2 because it's 5 electrons. And so this is 5 times 2, this is 10. The other we have to multiply by 5 because it's 2 electrons. So 2 electrons times 5 gives us 10. So we want 10 electrons consumed and 10 electrons produced. The electrons have to balance. This is one of the main differences between, let's say, acid base and redox. Redox, you're going to have an odd number of electrons, which we have to balance, and then we'll put it together like that. So it's the balanced skeleton reaction. However, this is, these occur, we didn't have to use the full skeleton method because those we could just copy off the redox chart. What if we had something that wasn't on the redox chart? So let's get a problem that's not on the redox chart. Let's take one from the book. So let me grab one from the book. Just one moment. All right, so I grabbed a number 47 from our book. And number 47 is a skeleton redox. Skeleton redox, we're given the major reactants again and the major products. And so when we look at this, we have oxalate, which goes to CO2, and we have permanganate, which goes to manganese 2. Permanganate to manganese 2, we just saw that one. That one's on the redox chart. So we didn't just copy that off the redox chart. That was permanganate plus 8H plus 5 electrons goes to Mn2 plus 4 waters. Now, this is gaining electrons, so this is a reduction half reaction. The reduction half reaction, which we copied directly off the table, shows this as our oxidizing agent. Our oxidizing agent will be permanganate and H+. However, the oxalate goes to CO2 is not on our chart. And so let's go ahead and figure that one out. So we take oxalate, this is going to go to CO2. And so we're just going to first balance the carbons. All elements, we balance all elements other than oxygen and hydrogen. And so that leaves us 2 carbons on the left and 1 carbon on the right. Now we balance this not by adding carbons. If we add carbons, that's going to change what's present. The way we balance it is we just change the coefficient on CO2. We'll make it 2 CO2s. If we have 2 CO2s, that's going to give us 2 carbons, and that's going to balance things out. Okay, then after that, we balance the oxygens. So over here, I have 4 oxygens. Over here, I have 4 oxygens. So it looks like the oxygens are balanced. We don't have to worry about that. Then we balance the hydrogens. So I have no hydrogens on the left and no hydrogens on the right, so that's balanced. Then we balance out the charge. So there's -2 on the left and 0 charge on the right. So we balance out the charge by adding negative charges. Those negative charges are going to be electrons. So this is going to be +2 electrons, and that would give us -2 charge on both sides. Now we add it. Now when we add this, we see we have 5 electrons here, 2 electrons here. So what that means is the top one we're going to have to multiply by 2, the bottom one we'll have to multiply by 5. So multiplying the top one by 2, we're going to have 2 permanganates, 16H+, 10 electrons, 2 Mn2+, and 8 H2O. And the bottom one we're going to multiply by 5. So that gives us 5 oxalates, 10 CO2s, and 10 electrons. And then what we're going to do is we're going to combine these two. And so when we combine those two, we end up with 2 permanganates plus 16H plus 10 electrons. Okay, that's the reactants from the reduction half reaction. And then let's look at the reactants from the oxidation half reaction, which would be 5 oxalates. And so plus 5 oxalates, C2O4, 2-. This is going to produce, now let's combine the products. The products are going to be 2 Mn2 plus 8 H2O liquids plus 10 CO2 plus 10 electrons. Now, what has to happen are the electrons have to cancel. So 10 electrons on the reactant side cancel 10 electrons on the product side. That works out. Then we look at, can we cancel anything else out? It looks like we can't really cancel anything else out. And so overall, the net reaction is going to be this. Let's do it in blue here. 2 permanganates plus 16H plus 5 oxalates is going to produce 2 manganese plus 8 H2O liquids plus 10 CO2 gas. Now, we double check if it's balanced. The way we double check if it's balanced is we just make sure that the atoms are balanced and the charge is balanced on both sides. And so let's check the atoms. Two manganese, 8 oxygens plus 4 times 5 is 20. 28 oxygens on the left, and then we have 8 plus 20, 28 oxygens on the right. 16 hydrogens, 8 times 2 is 16 hydrogens, 10 carbons, and the atoms are balanced. Then we check the charge. Minus 2 plus 16 is plus 14, plus 14 minus 10 is plus 4. And then 2 times plus 2 is plus 4. So this is balanced. And so that's the way we double check. It's easy to make addition errors, so you should always double check to make sure things are balanced. And so one of these half reactions we copied from the chart. The other we had to derive the half reaction for oxalate getting converted to CO2. Now, the next one here is skeleton redox. So we're given the major reactants and we're given the major products. However, none of these occur on our redox chart. So tin goes to this, and nitrate goes to nitrogen dioxide gas, nitrite. And so we're going to separate that into 2 half reactions. Tin goes to H2SNO3, and then the other half is going to be nitrate goes to nitrogen dioxide. And so nitrate has a charge. Nitrogen dioxide, there's no charge there. And so first off, we're going to balance out the tins. Well, the tins look to be balanced. And so that's already balanced. And then we're going to balance the oxygens. And so 0 oxygens, 3 oxygens over here. And we balance it by adding waters. So we need plus 3 H2O over here. And then we balance out the hydrogens. So that's 6 hydrogens here and 2 hydrogens here. So we're going to balance these by adding H+. And so plus 4H+ should bring that up to 6. And then we balance out the charge. And so balancing out the charge, I have 0 charge. This is tin's neutral, water's neutral. And I have plus 4 charge over here. And we're going to balance it by adding electrons. So this plus 4 electrons, we bring that down to 0. Okay, then we're going to combine everything here. And so it's going to be SN plus 3H2O, 3H2O. This is going to go to H2SNO3 plus 4H plus 4 electrons. So this is losing electrons. So this is oxidation. So this is the oxidation half reaction here. This must be the reduction half. This is gaining electrons over here. So we balance out the nitrogens first. So the nitrogens are already balanced. So that's good. Then the oxygens. We have 3 oxygens versus 2 oxygens. So we balance it by adding water. And so we're going to need plus an H2O. And then we balance out the hydrogens next. And so there's 0 hydrogens here, and we have 2 hydrogens over here. And so we need to go plus 2H pluses, plus 2H+, and then we balance out the charge. So minus 1 plus 2 gives us plus 1, and then over here, we're going to have 0 and 0 goes to 0. So this has got to be a plus 1 electron. So plus 1 electron. All right, so adding it up, we're going to get nitrate plus 2H plus 1 electron gives us NO2 plus H2O. So let's just check that these are balanced. And this is going to be the reduction half reaction here. Checking if it's balanced, let's check the atoms first. Tin, 1 tin, 6 H's, 4 plus 2 is 6 H's, 3 oxygens, charge. 0 and 0, 0, 0 plus 4 is plus 4, minus 4 is 0. So this is balanced. Looking at the reduction half reaction, 1 nitrogen, 3 oxygens, 3 oxygens, two hydrogens. Charge minus is -2, +2 is 0 is 0. So both of these are balanced. Okay, then we look over here. We have 4 electrons here. We have 1 electron here. So all we need to do is multiply this one by 4. So this is going to be 4. This is going to be 8. This is going to be 4 electrons here. This is 4 NO2 and 4 waters. Okay, now we can add them up. The electrons are balanced. And so this is going to give us Sn plus 3H2O. That's the reactants on the oxidation half reaction, plus the reactants on the reduction half reaction. 4 nitrates plus 8H plus 4 electrons. Okay, then let's add up the products. The products on the oxidation half reaction are going to be H2SNO3 plus 4H plus 4 electrons. Okay, and then the reduction half is going to give us plus 4 NO2s plus 4 H2O. All right, now let's go ahead and cancel the electrons. 4 electrons on the reactants, cancel 4 electrons on the product. We can also cancel some other stuff. I have 4 H pluses on the product and I have 8, so I'll cancel 4 of the 8 there. What else can I cancel? Waters I can cancel. I have 3 waters here. I can cancel out 3 here, and that leaves me with 1 water left over. And so I don't think I can simplify anything else. So I'm going to have tin. This is tin metal, which is solid, plus 4 nitrates, plus 4 H plus. Yield H2SNO3 plus 4 NO2s plus an H2O. NO2 is a gas, brown gas. H2O is liquid. Everything else is aqueous except for tin. All right, now let's double check that this is balanced. Okay, and so we'll check atom balance first. So 1 tin, 4 nitrogens. 4 nitrogens, 4 times 3 is 12 oxygens. So 3 plus 8 is 11, plus 1 is 12 oxygens. 4 hydrogens, I have 2 and 2 is 4 hydrogens. So the atoms are balanced. Let's check the charge. -4 plus 4 is 0, and this is 0. So this is the balance redox reaction. So we take the oxidation half and the reduction half, and we get the redox here. And in the oxidation half, this is the reducing agent, and the reduction half, this is the oxidizing agent. Here. All right, so that's skeleton redox, the last part of chapter 19. Okay, and so I'll talk about these more next week, but thanks for watching these. Bye.